Good morning, everybody. You're welcome to Chemistry 156 class again this morning. My name is Dr. Olatunde. I'll be taking you through atoms, molecules, and intermolecular forces. By the end of today's class, the notes and the slides for the class will be shared on the LMS page. So we start with the introduction. These are the outline that we're going to go through. We're going to be discussing the atomic nature of matter. We're going to look at the differences between the modern atomic theory and Dalton's atomic theory. We are going to be looking at the experimental evidences for the atomic structure, how the atomic structure is composed of the neutrons, the electrons, and the protons. And we are going to also briefly discuss isotopes and atomic masses. I'm sure that these are things you have done before in your various secondary schools. It will be like a brush up, and we'll just build a little more on it. And then we talk about the use of the mass spectrophotometer. We'll consider the electronic structure of the atom. We'll look at the relationship between electrons and light. Then the configuration of the electronic structure of an atom. We'll also briefly look at the covalent okay. And lastly, we'll discuss the intermolecular forces. Most of this topic, and even all of these topics are in your physical chemistry, the recommended physical chemistry. So let's start. By way of introduction, the atomic nature of a particular matter started as an hypothesis. It was proposed as an hypothesis since as long as 400 BC. But the first recorded ones were by Greek philosophers, namely Democritus, who proposed that if a single matter, any kind of matter it is, whether it is in a solid phase, is in a liquid phase, or gaseous phase, if you take that particular matter and you keep breaking it down into smaller and smaller pieces, you will reach a particular point where you get the smallest particle that still possesses all the properties of that parent matter, has all the properties of the parent matter. And he gave the name atomos, which is a Greek word for indivisible. And that's what it means. So that's where atom is derived from. And after that, it's an hypothesis. I mean, philosophy, that's not proper science. Somebody just think and reasons. That's what philosophy is all about. Somebody thinks and reasons that, oh, this is what it is. But then, in science, you need to propose, suggest a theory that could be tested And that is where we start with Dalton's atomic theory that are based on some tested laws, like laws of conservation of masses, law of constant composition, law of multiple proportion. These are laws that you are familiar with. You remember the Charles law, the Boyle's law, all those normal chemistry laws, basic chemistry laws. So these are the three fundamental theories based on the three fundamental laws. The first thing is agreeing with that philosopher, Democritus, that all matter is actually made up of tiny and indivisible particles. I've explained that, called atoms, and that atoms can neither be created nor destroyed. This is derived from the law of conservation of mass. What that is telling us is that at the end of the day, when there is any reaction, you can account for what you started with and what you ended with. Nothing comes from nowhere. That is where, when you write a chemical equation, it has to be balanced. Even though you form something new, but there should be balance. Nothing just happens strangely. Okay, so atoms can either be created or destroyed is based on the law of conservation of mass. That atoms of the same elements are identical and have the same mass and chemical composition. That's chemical properties, law of chemical constant composition. What we are saying here is that you can find oxygen anywhere, whether you find it in water, you can find the same oxygen in here, you can find the same oxygen elsewhere. As long as it is the same element, the atoms are going to be identical. They are going to be similar, and they will behave the same way. That's what it means by chemical properties. It will behave similar way. Law of constant composition. The composition of that atom is constant, irrespective of where it is, as long as they are atoms of the same elements. For example, you will find some elements having different kinds of atoms. We'll get to that when we talk about isotopes. You have carbon 12, carbon 13. So, for example, if carbon 12 forms CO2 and carbon 13 forms CO2, it's going to be, their properties are going to be similar. And lastly, the law of multiple proportion, the atoms of elements combine to form compounds in small number ratio. Well, as you will see that these are theories, these are fundamental theories on which chemistry stands upon. But as knowledge increased, some of these theories, there are some findings that brings some of them into question. Are you with me? That, I mean, we are saying that the same atoms of the same elements are identical. We are not considering the fact that, yes, we have C12, that's carbon 12, and carbon 13. Even though they will behave, they have the similar properties, but they are still a bit different, because one of them will have more protons and neutrons than the others. So that gives rise to the next slide, which is the modern atomic theory. So we now consider differences between the Dalton's atomic theory and the modern atomic theory. In Dalton's atomic theory, we say that the smallest particle of a particular matter is an atom. But from further knowledge, we know that we can find in an atom subatomic particles, some of which I've mentioned that I showed there. We have electrons, the protons, the neutrons, the positrons, the mesons. I have highlighted electrons, protons, neutrons, because in this class, we are going to deal much further with them. So we have electrons, protons, neutrons, and so on. And each of these can actually exist on its own. Each of these can actually exist by itself. So we can have a proton standing, for example. You'll have had what we call proton, for example, in chemistry, is an hydrogen atom that has just one electron. I mean, one proton, sorry, no electrons. So that's a proton. So H1. Normally, hydrogen is supposed to have, in its neutral sense, is supposed to have one proton, one electron to be balanced. One, H plus, rather, has only a proton, no electron, and it exists. It can exist by itself. And so also we have electrons and neutrons that we can exist. So we have subatomic particles. The second one, talking about atoms can either be created or destroyed, which is right. But from radioactivity, we have spontaneous emission of some nucleus that results in actual new atoms. At the end of the day, if you look at it very well, you will see that the equation is still balanced. You still have the same number of electrons in totality and the same number of protons, but you create ultimately something different. For example, in that equation, you see there, with uranium, we ended up with thorium and helium. Unlike the normal chemical equation, when you have maybe sodium chloride reacting with an acid, let's say H2SO4. I'm sorry, sodium hydroxide reacting with an acid, let's say sulfuric acid, and you end up with sodium chloride and water. Everything you have in that equation that I mentioned now, when you have NaOH, sodium hydroxide, plus sulfuric acid, H2SO4, and you end up with Na2SO4, sodium sulfate, and H2O, for example, everything that is in that equation that I mentioned is within the equation. We are revolving around the equation, and Dalton's atomic theory takes care of that. But in radioactivity, you create something entirely new, like you have that in that, because when the nucleus of uranium emits an alpha particle or a gamma particle, you create another nucleus that belongs to another atom. So in radioactivity, we say that we can create a new atom, but at the end of the day, we still end up with a balanced equation such that we can account for the matter. It's not as if at the end of the day, as you can see there, the mass number of thorium is 234, that of helium is 4. If you add that together, it gives us the mass number of uranium, which is 238. So the third atomic theory proposed by Dalton, talking about identical elements, is being questioned by the existence of isotopes. Isotopy is a concept where you have the atoms of the same element that have the same atomic number. That is, they have the same number of protons they have, or electrons, but different mass number. That means they have different number of neutrons. So, for example, we have those mentioned listed isotopes for oxygen. So we have oxygen 16, oxygen 17, and oxygen 18. They are all oxygen and can react the same way as with each other. They can be used interchangeably. Most of the time, one of them will be more radioactive than the other, and it can be used for monitoring things. They have their different usage anyway. but they can react similar ways. The last theory is that which says we have atoms combining in small, that small is the issue, whole number ratio. And the concept of catenation, where you have giant molecules being formed. As at the time when Dalton's atomic theory, you can see the year on the slide, 1806 to 1896, that's 5 years. You can see that, I mean, within the limit of what was available, the information available gave rise to that theory, but as knowledge increased, the fact that we can find giant molecules, for example, hemoglobin, things like sucrose, at least that one is you are familiar with it. You can find C12O22, H11. So you can find giant molecules being formed, and things that has carbon atom, molecules or compounds that have carbon atom especially seem to do this a lot. It's not only limited to compounds with carbon atoms anyway, just like the hemoglobin that I mentioned. So the next thing we would like to talk about is the experimental evidences for the subatomic particles that we talked about. So what gave rise to the fact that we said, okay, we can stop, the Dalton's atomic theory stopped with atoms, and then the modern atomic theory, that now you can note that the modern atomic theory is not limited, I mean, was not named after just one person, because each of those deviations were discovered by different scientists all over, not limited to just one person. So many people did something, you just somebody just finds out something one day, and another group finds the similar thing out, and it begins to put question on each of those theories. So, and then, and like I said, that we now have subatomic particles, which are one of the things we are going to major on in this particular class. I will start with electrons. I told you we are going to talk about electrons, protons, and neutrons majorly. For positrons and mesons and others, it's not within the scope of our class here. So it starts with William Crookes in the 1870s. He was just carrying out a normal experiment where he passed high voltage of electrical discharge through various gases, at low pressure in a sealed tube. Now, note all those content of that experiment. He will put various gases in a sealed tube under low pressure, and he was passing electrical discharge through them. And he constantly found out that there was a beam of ray that came out from the negative electrode. Since he was carrying out electrical discharge, you know that he's going to have an electrode, a cathode and an anode. So he found out that there's a ray of light that kept coming out from the negative electrode, the cathode, and is always hitting the negative electrode, the anode. You know, as usual in science experiment, you record your observation. You don't just come to a conclusion from your observation, but you perform different tests on the observation. It is then you can infer, come to an inference or a conclusion that, oh, if this is this, then that is that. So from the beam of light that he kept observing, moving from the negative electrode and hitting the positive electrode, he decided to call those rays cathode rays, because they were emanating from the cathode and hitting the anode. So that was why he called them cathode rays. this is just a figure, a diagram showing his experiment. That's a sealed tube that you have there. This is the sealed tube. And you have the cathode, the anode, and he notices the direction. And you will soon see how he knew that it was emanating from the cathode to the anode. And he called it cathode ray. Now, I just put it down as a schematic diagram of what he has. The same thing. So that's of the discharge. This vacuum pump is to ensure that the gases are under low pressure. So he's the one that will introduce the gas, and the gas of, and when I say gas, the gas can be oxygen, it can be helium, gases of different kinds of elements. But the ones that, if you note the year, I said 1870. So not all the elements have been discovered as at then. There were limited elements. So the ones that were available were the ones he was working with. So let's look at the characteristic of the cathode rays that gave rise to what we have now as electrons. He first of all discovered that they travel in straight lines. This he knew because he puts like a metal cross, or let's say a particle, in the path. And he found out that it casted a shadow directly at the back. So this is like a shadow. This is like a shadow of the metal that is put in the path of the ray. So this is where the shadow. So that will give him number one, an idea of the direction it's coming from. You know, if you face the sun, your shadow will be at your back. That's kind of a thing. So this is where, so this is, the thing is coming from this place, hits this, then the shadow is casted here. And also that it is traveling in a straight line. Because if this ray were not traveling in a straight line, there was no way it could hit this and produce this kind of shadow. That's the first thing. Then it discovered by putting a paddle, a light means not heavy. In this time around, this is what we mean. Can rotate. It says here that a light paddle can rotate, if it's placed in the path. So when these cathode rays hits this paddle, the paddle begins to rotate. That's the direction of the rotation. So this gives, it can conclude from here that the cathode rays so that's why it has energy enough to hit this and cause rotation. The third experiment he carried out on the cathode ray was finding out, he wants to find out what kind of charge is there. So he placed both electric field and magnetic field. He subjected the rays to both magnetic field and electric field. In an electric field, this is an electric field. We have the positive plate of an electric field, the negative plate of an electric field. The rays are deflected towards the positive terminal in an electric field. So that gives him the kind of charge. If it was deflected towards the negative charge, it will, towards the negative plate, it will mean that the charge is positive. You know, unlike charges attract. So this is a positive plate placed here, and you can see that the cathode rays, forget the fact that we have written electron here. At this time, at the time of the experiment, it has not been called electrons, but it was his observation that when it placed an electric field in the path of the ray is deflected towards the positive plate. And this tells him that it's likely a negatively charged particle. We have said the other time, the last experiment tells us it's a particulate entity, not just air. That's why it was able to, not just something that, not just vacuum, that's the better word, not just vacuum. That was why it was able to cause the light particle to rotate. Then in a magnetic field, it is rotated in the opposite direction. So that gives us an idea that it is a negative. So I bring all these characteristics together. Other characteristics of the cathode ray is that irrespective of the material of the electrode, so you can make the electrode from different kinds of metal, or the gas that is put in there, all the observations were consistent, and that the cathode ray also has the ability to penetrate small thickness of matter. So all these brought together gives us an idea that whatever it was that it is negative, and all the characteristics that, because you may be asked to, come up with the reason why he made his final assumption. That was William Crook. Now, science and chemistry especially don't just deal with qualitative experiments. You must be able to quantify whatever it is that you do. So to give value to this negatively charged entity that we have talked about, many people worked on it, but the one that we are going to consider, which is the basic and fundamental one, is that done by Sir J.J. Thomson in 1897. He was the one that William Crook gave us the qualitative characteristics for the electron. J.J. Thomson was one of the people that gave us the quantitative characteristic of the electron. And that's what we'll quickly do in the next few minutes before today's class ends. The summary of this is on this slide, but I will take you through each one by one. And note this year, the most important thing is to know, okay, we have a negative particulate entity. What is the mass? Since the same thing is observed in whether you put whatever gas you put there, so it must have a particular value, a mass. But how do you measure a mass of something you cannot hold, as at this year? You can do that now, but as at 1897, that was seemingly impossible within the limits of knowledge available. So what we will get at the end of this session is the mass to charge ratio, the value for the mass to charge ratio. So please go on with me. Now, I have said this in the last picture I showed about the characteristic of the electron. There is this experiment that J.J. Thomson carried out that is called the specific charge experiment. It is noted that a negatively charged electron or entity or particle will be deflected in an electric field. It will be repelled from the negative plates. Like I said, these are the negative, see, minus, all those minus I. So this is an electric field. This is an electron, that cathode ray, coming from wherever, and this is an electric field. These two bars, two blue bars, this is a field. We have the positive plates up there, we have the negative plates here. So if an electron or a negatively charged entity is subjected to an electric field, it will be repelled from the negative plate. You can see as it got here, it is being repelled and attracted towards the positive plate. That's Sir J. James Thomson's experiment. All these specific charge experiments are Sir J. James Thomson's experiment in 1897. Now, this is a magnetic field. The green circle here is a magnetic field. In a magnetic field, the same negatively charged entity, now an electron, so let's start calling it an electron now. They are deflected in a circular arc and in an opposite direction. A circular arc, an opposite direction to that of the electric field. So if the electric field was this way, was up, in the magnetic field, it will be down. If we have reversed the electric field, let me go back. If the positive plates were down and the negative plates were up, we will not get it this way. It will have come like this, come down. So if you now subject it to a magnetic field, it will be in the opposite direction and in a circular arc. That's what we are trying to say here. So electrons are deflected in a circular arc in an opposite direction to that of an electric field. Now, imagine us putting both the electric field and the magnetic field together at the same time. When both fields are present, the forces cancel out and it travels in a straight line. So by adjusting or varying both the electric field, so he knows the amount of the electric field or the magnetic field that is trying to put there. So he knows the amount of the electric field, he knows the amount of the magnetic field that is trying to that is introducing or subjecting the electrons into. So at each time when the electron is allowed to move into both an electric field and the magnetic field by adjusting them, he was able to calculate. See, this is a modified cathode ray tube that by J. Thomson, in which both this is a magnetic field and an electric field. So he can adjust the electric field, then he would monitor the deflection. It is only when both of them are equal that it travels in a straight line and he is able to monitor the degree of deflection here on this end. So he modified the cathode ray. He subjected an electron to both an electric field and magnetic field. So now let's look at the mathematical implication of what J. Thomson did. He balanced the cathode rays between the electric and magnetic forces. So if let's say the force on a charged object in an electric field is F, this force depends on the strength of the electric field E and the charge on the object. All these are inside your physical chemistry textbook, the one we recommended, especially the one that was put together by the lecturers and chemistry department. And you can also get them in any other recommended chemistry textbook. But I've just brought them out so that it could be easy for you to comprehend. So it's not something new. And I'll make the slides available at the end, but I would like you to follow me. So, like I was saying, in an electric field, the force F is equal to the electric field strength multiplied by the charge. In a magnetic field, the force F depends on the magnetic field strength. This one is B multiplied by the charge and the velocity. I apologize for this box that is showing here. It's a default box. It's an error on the computer, and if I try to change it, it will change a lot of things. So pardon me for that for today. Next class, I'll make sure that it's removed. That's why you find it coming and going. This box that is saying please remove. It's a fault on the computer. Sorry about that. So like I said, so you have F equals to BeV, where B is the magnetic field strength, magnetic field, the strength, yes, the charge E, and the velocity of the object. Now, since the forces were balanced, so we have the electric field force equals to the magnetic field force. And if we bring the velocity out, you will get this equation. You can get that. Since the charge on the object is equal and you can cancel that out, so the velocity is equal to the strength of the electric field divided by the strength. So that means that we have something here. Sorry, that means we have something that we can measure. Since we can measure the magnetic field, we can measure the electric field. That means we can velocity. Since the two fields could be measured, we can then calculate the velocity of the cathode ray, and it can be used for further calculations. So for the further calculations, because we want to get a particular value, I told you charge to mass ratio or mass to charge ratio, whichever way you like to talk about it. So in a magnetic field, remember we said that it moves in a circular arc, and the arc has a radius r. If the centrifugal force on the electron has a mass m in the magnetic field, then the centrifugal force F equals to mv squared over r. You are familiar with centrifugal force. This is not new to you. And recall that in a magnetic field, we said F equals to BeV. So if we equate this, this is a force, the centrifugal force on the electron in the magnetic field. And the electric field force, the magnetic field force is also this. So all these are inside the magnetic field, the BeV, the mv squared r. If we equate that, we can get the charge, which is E, to mass ratio. Just make E over m the subject of this formula, and you end up with E over B squared R. And remember, we can measure the charge, we can measure the electric, both the electric field strength and the magnetic field strength, and we can determine the R of the radius of the arc, which is usually constant, and then we can have a value for the charge to mass ratio of an electron. The charge to mass ratio of an electron, and is given by 1.7586 times 10 raised to power 11 coulombs per kilogram. So I would just like to end here for today, so that we don't take too many calculations in, because we are going to be talking about how then do we get the actual charge. You know, what we have here is charge to mass ratio, charge to mass ratio. So that we get the actual mass of the. So if you want to ask a question, I would try and unmute you now. When I mention your name, I see too many hands. I don't know how to handle. These are too many hands already. Okay, so let's start with them. Just a moment, please. Samuel Oyelami, can you unmute yourself?
Yes, ma. Good morning, ma.
Good morning.
Okay, I want to ask a question about
Hello.
the electric so that can we place randomly the poles of the magnetic? Should I continue?
Continue. Your
Hello,
network is
hello, ma.
unstable. I can hear you. Samuel, I
Oh,
can hear you.
all right. Okay, all right. My question is, all right, my can we place randomly the poles of the magnet against the plates of the electric field, like placing the north pole of the magnet with the positive plate of the electric.
I would try and respond to that, to what I think you are saying, because I can't. Hello. Okay. Let's go back to I don't know what you are trying to ask. I'm guessing you are asking about how to place the experiment, whether we should place it, place the electric field away from the magnetic field. I'm not sure whether that is what you are asking, but remember what he wants to do. Even look at this. Look at the modified cathode ray. This is a magnetic field. This is the electric field. It's not as if it's placed together. It's just that they are meant to. It is subjected to the field at the same time. It's not as if you just only do the electric field or magnetic field. You make sure the essence is to balance out the field, to vary the electric magnetic field and the electric field at the same time. So as it's coming through the magnetic field, the electric field is balancing it. So it's not as if it's going to be placed on top of each other as experimentally. Experimentally, look at the modified cathode ray. It's not as if both the fields are together. So I don't know whether I've answered that. I'm going to ask Israel Babajide to unmute. Israel, are you there? Do you still want to ask question?
Good morning, ma'am.
Good morning.
Yes, ma'am. Ma'am, my question is this, ma'am. You said the magnetic force, which is F is equals to BeV, is equals to the electric force. For
it to be balanced out, yes.
Yeah, ma'am. But for a magnetic force, which is a circular part, and a force in circular part is in centripetal force. So when you now equate the magnetic force, which is F equals to BeV, equals to the centripetal force, I know for a magnetic. Okay, yeah. Now I can, yeah. So for an electron in a magnetic field, it has a F equals to BeV, which is equals to the centripetal force, the circular, the time taken for the let me say the part through which the force through the electron has moved in a circular part. So when you now did the charge to mass ratio, which is EM is equals to E over B squared, I don't understand how you arrived at that.
Okay. Just give me a minute to answer that question. Okay, if you look at this equation, let's go back to this equation. I'm guessing that you don't have a problem with the previous equation. Since what we are saying here is that this is the electric field strength. This is the magnetic field strength. The electron is subjected for this to happen, for what you have in that cathode ray to happen, for this to happen, for it to be like this, this strength must be equal to this. Look at this. Look at this here. You can see that this is not balancing out. They have, okay, here we have only the electric field, here we have only the magnetic field. But if you put the two of them together, and they are equal, that is when you will have a balancing out. I will try and show an animation maybe in our next class to see that if they are not, if those forces are not equal, it doesn't balance out. It doesn't give you a straight line. It will still deviate. It will still deflect. Anyway, so I'm sure you understand how this is. But now, this being said, in a magnetic field, the centrifugal force is still, which is still being exerted on that electron in a magnetic field, is still mv squared r. And since it's also a force, we can still equate it to the magnetic field strength, which is also a force. The two forces, this mv squared r and the BeV, are in the magnetic field. And that was why it was equated here. To get E over M is easy. Just bring M to this side and the BV to that side. If you bring M to this side, it becomes E over M. The BV comes here, so we have V squared over BVR. It cancels. Hello? Are we together? Let me see somebody else. It's already like 2 minutes to the end of the class. So let me just ask somebody else to talk. You are still raising your hand. Okay, I've asked you to unmute. Hello?
Yeah, ma. I understood the way you.
We have to give room for other people. Like 20 people are raising their hands.
Okay,
in fact, I'm saying 20, like 40 people are raising their, okay, no, just like 20. So please.
Okay, I've had.
Go ahead. Go ahead.
Okay, I should go ahead, ma.
Yeah.
Okay, ma. I said I understood the way the magnetic field strength is equal to the electric field strength. I understood it. But what I'm saying here is that there's another, when you said the E, BeV equals to mv squared r. Now we have E over M. This capital E, I don't know where it's coming from. The capital E over BR squared, B squared R.
Sorry. Okay, let's go back. Okay, I'll quickly do that now. I'm really sorry about that. Let's go back. If we put E over M here, we have V squared over, I should have done it one by one. We have V squared over BVR. So if we come back to this equation, come back to, sorry about that. The equation, I'm trying to go to the previous slides. Okay, yes. V is E over B. Sorry about that. What I will do is that in the next, permit me, because I can't write it now, permit me to come to the next class and derive it one by one and write. If you just substituted this what you have gotten here for V into that equation, you know that V is not showing here again in the next, let me, but you know, V over B, VR, there will still be one V. What you have before, one of the V here, you have V over BR. And if you bring that from that other equation where we have V equals to E over, that's where you have E over B squared. Do you get that? Let me ask you again. Do you get what I'm saying? There was a step I missed here that I omitted, thinking it was given. Normally, if you have from this equation, you have E over M, equals to V squared, Abby, over BVR. One of the V on in the denominator will cancel one of the V's in the numerator. So you end up with V over BR. If you go to this previous equation, so but V equals to E over B. So if you bring that back into this equation, you will now have E over B squared R. Now let me ask you again, because I'm guessing maybe that's why what some people, do you understand that?
I understood. Good, great man. That's what I'm confused about. Now I understood.
Okay.
Understood. Thank you, man.
Okay. Let's see. Just to phone me, you are the last person that will ask. It's already time. Okay. Just to phone me, you can ask your question. I've asked you to unmute so that we can go.
Good morning, ma'am.
How are you?
I'm fine, ma'am. Ma'am, please, I want to ask, you said the comparing of the former Dalton's theory and the present modern atomic theory. Do the modern atomic theory cancel out the Dalton atomic theory, or do they stand?
Okay, good. Very, very good question. The Dalton atomic theory is still there, but there are questions. You know, when a particular theory, when there are questions raised about a particular theory, you set the theory aside. The theory becomes null as long as there is a contrary what do I call it now? Proof based on experimental findings that contradicts the finding of that theorem. So, but we still have the law of constant composition. It doesn't change. The law of multiple proportion, the law of conservation of mass is still there. But based on, okay, like saying that the smallest indivisible particle of an element is an atom is not completely right, but it's not a false either. The only thing is that we have subatomic particles and all the other things that I pointed out. So there are the modern atomic theory is what you if you want to be to refer to the atomic theories that chemistry is based on now, we refer to modern atomic theory. Without, it's not as if Dalton atomic theory was wrong, but within the limit of the information that he had at that time, that was all he had, and it was right as at that time. That was why it was accepted. I think this is a safe place to end today's class. It's been nice meeting this class. So see you tomorrow. I would improve on this particular side so that you don't get further confused. It's just that I omitted a step or two. See you. Thank you very much.